Hello and welcome. This is my presentation, Rhenium Gets Lit, a photochemical route to oxidative addition based on the paper Oxidative Addition of Haloalkanes to Metal Centers, a Mechanistic Investigation by Harrison and Annette as part of the CH232 module. In this slide, I'll be introducing some general ideas and giving context to some of the topics related to the reaction. First of all, studying the relationships between haloalkanes and transition metal complexes is very beneficial for many reasons. Firstly, and more obviously, are its uses in organometallic chemistry. One such use is or via the process of oxidative addition, and that allows strong bonds such as carbon halide bonds to be broken, whereas other processes wouldn't be able to break these bonds. So this is very good for breaking these bonds. It's involved in synthesis of pharmaceutical compounds and other complex compounds, just to name a few of its uses. Another factor is cross-coupling. This allows different organic compounds to bond together, which forms more complex organic compounds that would be hard to synthesize otherwise. Another important use of these studies are to use them to combat environmental problems such as groundwater contamination. Polychlorinated solvents, such as, or which are usually industrial or agricultural solvents, such as pesticides, contaminate groundwater and they also contribute to the destruction of the ozone layer, which increases global warming. And they're very difficult to remove and destroy. So, understanding how they interact and bond with transition metals is very crucial to developing sustainable ways to break down these pollutants. In this slide, I'll be talking about the overall reaction. So you start with the cyclopentadienyl rhenium CO3 complex, and from there, dichloromethane, which is the solvent, is added under a specific wavelength of light to form the intermediate. From there, the intermediate undergoes a radical mechanism to then form the final product. So in a little bit more detail, when the initial complex is exposed to photons with a wavelength of 266 nanometers, the complex loses one carbon monoxide ligand to briefly form a sigma adduct with dichloromethane. The dichloromethane acts like a Lewis base, with one of its chlorines donating a lone pair towards the rhenium. This is the sulfate complex intermediate, or this forms the sulfate complex intermediate, as the solvent molecule, which I mentioned earlier, is the dichloromethane, which weakly bonds to the metal center. For part two, or step two of this reaction, the rhenium cleaves the chlorine from the dichloromethane, leaving the dichloromethyl as a radical. These two radicals quickly bond to form the complex. So, as for oxidation states, the oxidation state of the rhenium remains constant at +1 during the first step. However, in the second part of the reaction, it changes from +1 to +3. This is because in the intermediate complex, the dichloromethane ligand is neutral, and so it only donates 2 electrons to the metal center. However, once the radical mechanism has been performed on the intermediate, both the chlorine and the chloromethyl anions give 2 electrons, totaling 4 electrons given. As the carbon monoxide and the cyclopentadienyl ligands don't change throughout the reaction, or throughout this past step, the total ligand donation increases, and so the oxidation state of the rhenium must change in order for it to obey the 18 electron rule. As such, the rhenium is oxidized from +1 to +3. On this slide, I'll be talking about the mechanisms or the potential mechanisms of this reaction. There's three possible mechanisms that were formulated for this reaction. So for the first one being an ionic mechanism, the second one is a concerted three-membered transition state, and the third one is a chlorine radical abstraction mechanism. So first of all, the ionic mechanism. In this mechanism, the chlorine donates a lone pair to the rhenium, forming a chlorine anion and leaving behind a carbocation. The carbocation would then eventually bond with the rhenium. However, it would do this if it had enough energy. This mechanism was ruled out because the energy required is drastically higher than the energy that was observed or measured during the reaction. For the second one, we have the concerted three-membered ring. In this mechanism, it involves the simultaneous breaking of the carbon-chlorine bond and the formation of the rhenium-chlorine and the rhenium-carbon bonds. This should reflect a low or even a negative entropy, as it should all be very ordered. However, again, this isn't the case, as the entropy is 11 EU, which is inconsistent with a mechanism like this. As such, this one was also ruled out. Lastly, we have the um, chlorine radical state mechanism, which consists of the rhenium removing a chlorine from the dichloromethane via radical cleavage, leaving the chloromethyl as a radical. These two radicals quickly bond within the solvent cage to form the complex. The free radical scavenger TMPO was employed in this reaction to observe changes in the reaction, of which there were none. So this supports in-cage recombination, as if it was out of cage, the free radical scavenger would have picked up something. The measured values also support that this is the correct reaction, as they line up with what should be expected, and so this mechanism was favoured and deemed to be correct. And there's just a few quotes at the bottom to support my statements. In this slide, I'll be talking about analytical methods and how they can and are used to infer electronic structure within intermediates and other parts of the reaction. So first of all, in the intermediate complex, the carbon monoxide ligands produce IR peaks at 1946 and 1874 centimeters to the minus one respectively. And then in the final product complex, again, they produce peaks at 2043 and 1600 or 1967 centimeters to the minus one respectively. These equate to changes of roughly 100 centimeters to the minus one increase, which is characteristic of oxidation of rhenium from 1 plus to 3 plus. It also shows that IR spectroscopy is sensitive to electron density and changes in ligand environments, and it shows that rhenium has become more electron deficient. In order to actually observe these changes using IR spectroscopy, the reaction was kept at 213 Kelvin, so very cold, as the intermediate is relatively stable and lasts about 30 seconds at room temperature, so that's not long enough for them to do tests on it. So they keep it at 213 Kelvin, which allows time to observe changes in the reaction, as well as differentiate between the intermediate and the final product. So to conclude this presentation on this paper, we've learned that photochemical activation of the initial metal complex leads to oxidative action of, in this case, dichloromethane, but it can just be any haloalkane via a radical mechanism. And in doing so, the oxidation state or the transition state of the metal center will increase. In this case, it was from +1 to +3. We know it's a radical mechanism by the IR spectroscopy that was obtained and the thermodynamic conditions that were measured during the reaction. They support these claims. So this whole reaction, we've learned that it is used to break carbon-chlorine bonds or any strong bond, but in this case, carbon-chlorine. This gives us many uses for this reaction in different fields, such as in organometallic chemistry. It can be used in catalysis or in making pharmaceuticals or other complex compounds. And another field it can be utilized in is combating environmental impacts, such as breaking down pollutants before they are released into the environment, such as CFCs before they are released into the ozone layer and break it down, or breaking down haloalkanes before they infiltrate groundwater and pollute that. And the paper also states that when pentamethyl cyclopentadienyl ligand was used instead of cyclopentadienyl, so with the methyl groups, that increased the rate of reaction quite a lot, which backs the claim that the rate of oxidative addition increases with the electron density of the metal. Thank you for listening to my presentation.